Good afternoon, and our first speaker will be Jun Lee from Stanford, who will speak on
higher genus chromographing.
higher genus chromatography.
Thank you. I'd like to thank the organizer for the invitation. It's a pleasure to visit the Bronx and the East Coast. And I just missed the wind. Okay, so I'm going to mention a little bit about the prior progress of genus chromophorin invariants of quintic, and I'm going to mention a simple example of a wall crossing, and after that we will study how we try to work out the high genus chromophorin invariant of quintic using this wall crossing idea envisioned by Witten. And just not getting too excited, the major work is a joint with Yang Chen at Hong Kong. And this So first, let me just quickly review the progress in high chromophorin invariants of P4. So you should think of P4 as a special case of a toric variety, and a quintic, which is going to be W5 equal to 0, and for me, it will be finished fixed throughout. It is standard for my quintic. This is inside P4. So you should think of this as a complete intersection in a toric, smooth toric variety. So the question is, we want to say what is the prior progress in understanding the chromophorin invariants. Okay. So we know that, just spend a few minutes, I get some magic clause is that when we have the moduli space, P4E, moduli space of a stable map, C goes in this actually side, P4, and this is the F, right? And I will say stable if and only if the automorphism of this data is finite. So in other words, automorphism coming from automorphism C, but P4 is fixed. Automorphism C that commutes with this arrow is called automorphism this map. If the automorphism map is finite, this is stable. This is usually the first thing we try to construct a Riemann stack. So we take all G is the degree, G is the genus, and we take the domain connected, and this turns out to be the Riemann stack. And then we can construct perfect obstruction theory. That's because the domain is a curve, taking a nodal curve, and then we can have a virtual cycle, and which is inside. And we have we just calculate the obstruction ring theory, and you get the virtual dimension. I mean, this moduli space for high G is going to be non-reducible, and components have different dimension, even in G equal to 1. But the point is that we want to have a pure one. This is the virtual cycle. We're going to be inside G. And then we get the virtual cycle, and then we can talk about the chromophorin invariants. Then we can talk about chromophorin invariants of this particular integration over this cycle. You repair this cycle. This is a pure dimension cycle, P4D, with some topological class on M bar G, P4D. There's some class you can, on this topological space, and you can get something which is pure, and these are, in the general sense, chromophorin invariants. Okay. So Now after this one, then the question if you want to you can study the property, but today we really say how to compute.
So can you write bigger?
Oh, even bigger. Okay.
You don't need to, right?
To compute. So here I'm just saying P4, right? I mean, if you can say the same words, ask the same question for arbitrary smooth variety, but that's even harder. Okay, so quintet is already very hard, but for P4, the key point is that P4 is a toric variety. So we have a C star. You can think of C star to the power of 5 or 4. But let me just say, okay, let me say 5, which is right as a torus action. So this is a T acting on P4, right? If I have an action on this one, and I emphasize that this is a modular space is constructed. So if we have an action here, so the modular space P4B, I have an action here, then I'm going to have an action on this modular space. And then then we talk about the virtual cycle. Virtual cycle is constructed by using the obstruction theory, which is canonical in a sense. And every construction, everything I talk about construction is canonical. So actually this cycle is T equivariant. Okay. So we can actually get a T equivariant cycle inside a T, the equivariant cohomology of RG P4D. And then we have this wonderful formula, virtual localization formula. This is Graeber and Panner. So this is a virtual localization. I want to emphasize this. So the virtual localization gives you is that, okay, so now I write W to be my modular space. Then I can write the fixed loci, and I can decompose it. So these are, so we'll talk about it in a few minutes, just give a rough idea. So it's a disjoint unit indexed by something of the fixed. Okay, so these are fixed. And then the formula say that the virtual cycle, so this is the same W, okay? This is going to be equal to some, it's just like the Born localization formula. If you have equivariant class, you can calculate, and that class should be localized to the, to the fixed loci. So fixed loci has to have a contribution. So each contribution, so the fixed loci has a virtual cycle, and then it has to be, it's like the Born fixed point formula, but then you have to, everything has to go virtual, okay? So this is the Graeber and the Panner. So I just W gamma W, which is inside. So this is have to say T, but I have to localize of this U is inside. I mean that's after localization. Okay. So this is the fixed point, this localization formula. To give you an idea, how are you going to use this localization formula? For instance, example, Fc goes to P inside Wt. How they look like? If okay, let me just draw. Say it's actually, I think it's a P3, right? Not P. So this is a fixed point and this is a fixed line. So it's going to look like I have a high genus curve. And then there's a curve, and there's another high genus curve. And let me just draw this one here. And it has to be fixed, and this has to a point, the whole component to a point, and this is going to be this point, and then this line maybe goes to this line here, and this line, I mean this is a circle, this is P1, maybe goes to this P1 here, and this one may continue to goes to this, or go to this. I mean, that's a different way, but the point, the upshot is that the fixed loci you can really describe by high genus curve has to map to points, and then one genus curve has to go to invariant lines, and then and then maybe come with a loop and somehow. So the fixed data can be described by the combinatoric data. Of course, it's still very difficult to study. Apply this. It took quite a few years to eventually use this formula to solve the genus one mirror signature conjecture. So that's a long story, but I want. So that's the beginning. So what is the beginning for the genus 0? Oh no. So that's the beginning for the genus 0 P4 global weighted invariants. You do a virtual cycle, and you understand this invariant, and you come up with then you apply the virtual localization formula, and then you study the fixed point. So this is now. What about the next step? Right? What about Aufquintic? Aufquintic again is the genus 0. I just mentioned that you just turn out to be that if you took the genus 0 is going to be equal to inside 0 P4 D, and which is going to be F pulled back W5 equal to 0. So let me just for the later comment, you're all experts, so I will just write as a notation P4 W5 X15. This is the defining equation for the Aufquintic. So this is 5e plus 1, and then you have a section which is a pi direct image, pi direct image F pulled back over 5. This is vector bundle and rank in 5d plus 1 again. And this is the 0 section, so this one is just going to be Q 5d. Is the Euler class C5d plus 1 of pi over. And again, I have a torus action here, and this is a torus equivariant vector bundle. The section is not equivariant, but nevertheless, the Euler class is still equivariant class. So I can apply the virtual localization. No, this time you don't even virtual, just do a localization formula to calculate the Euler class over smooth Delignol stack, and that's how you get the Quintic with the number. So this is so far I'm missing another line to attack the high genus or genus 0 is by degeneration methods. Okay, so the degeneration into the simple crossing case, and also in the recent progress to degenerate to the normal crossing, thanks to the next speaker. We hope that the degeneration also will give us information. What I'm going to talk about is sort of using the localization and this idea. So I'm sort of emphasizing on this. So this is for the Quintic. So the Quintic, because the Quintic itself does not have a torus action. Okay? Anytime you have a torus action, you can use localization formula. This does not have a torus action. But in genus 0 case, I can write it as equivariant Euler class of a vector bundle for G equal to 1. Myself and Zinger has a sort of the modified version, which allows him to prove the genus 1 mirror symmetry conjecture. But the G seems to be very, very hard. And at least we are not pursuing this direction. Okay. So this is so far the current status. So what we're going to do next, in 90, this is the line brought to my attention. I was reading physics literature, but there's so much. So Yongbing Ryan brought to me this line of Witten, 93. Witten says, let me just very quickly say that. So there is a line, there's a 0 here, there's a sequence of series. Okay, there's a physics series, whatever parameterized by t, so that when t goes to infinite, ft is going to growth Witten of quintic. Okay, the quintic is the first Calabi-Yau system we want to understand. I mean, so this is really the thing we like testing. In a way, it's also the simplest possible. And then when limit t goes to minus infinite, it's going to be called LG series. I'll be more precise. So that's another series which it's hard for me to understand. And then he says that the whole series, the series from this and this is connected by, well, depending on how you do it, but as an algebra geometry. But I mean, this is, you can view it as some parameter associated with symplectic quotient, right? There's a moment map, whatever. But in algebra geometry, all of this become constant until then there is a jump. So there's a wall crossing. So in algebra geometry, we will just interpret this as saying growth Witten of Q5 and the LG of W5 are equivalent via wall crossing. Okay, so you can think of this as a constant series. So this become growth Witten, and this become the FGRW, the LG, and then there's a jump. And the jump is we always say this is a wall crossing. So the question is how are we going to use, so here is so I'm going to talk about the recent progress in constructing a model to study this wall crossing. And to begin with, I begin with a trivial example, or an easy example. GIT okay, so the thing I'm going to look at C6 acted on by C star. It's a diagonal action of weight 1, 1, and minus 5. So it's like a Calabi-Yau. Okay, so I just scaling by 1 at the first 5 coordinate and scaling by z t to the minus 5 power. So this is the action. And then I look at the quotient. And this, of course, this is an argument step, right? Because it has, so it has 2 GIT quotient, or good quotient. And this is I should be a little bit careful when I say, because this is just a fine space. But nevertheless, I can say there's a GIT topic quotient. And I take C5, take on origin, the first 5 copy, cross C, quotient by C star. So this actually is, I take this out, and I take this 30, this is a 30 for stack. And then there's another, maybe I have to be careful. Right? So the other one, I take out the 0 of the second one, cross C, take out 0, quotient by C star. And this, every point has only finite stabilizer, so I get a 30 for stack. And this, of course, we know is K P4, and this is just going to be, because the weight here is 5, it's C5 quotient by C5. Okay. So we say these two are two simple wall crossing GIT, so that's a GIT quotient. And now, how to study the wall crossing, the flip or whatever, the transformation between these two, so I construct a mass space. This is not necessary for this example, but it won't be useful. But the principle works for arbitrary sort of simple crossing of GIT quotient. So mostly this actually learned from Michael Sadis many years ago. And the thing you do is to C6 cross C2, and C2 should be a copy here. So let me write down the action here. So it's a Z1, Z5, and W, U1, U2. So T1 equal to T1, Z1, T minus 5, W, right? And then T, U1, U2. I mean, think of if this is the homogeneous coordinate of, because there will be a homogeneous coordinate of a T2, then my T2 action is exactly equal to no change, but then Tu1, Tu2. Okay, so I just cook up this one here, and I do so what is my W here is my master space, which I might use W, I mean, let me just use W, is going to be equal to, I mean, you work out of the detail, I mean, it's a very nice example. 6 cross C2 subtract, so I'll write this one as Z equal to U1 equal to 0. Okay, is this a locus? Union W equal to U2 equal to 0. Union with U1 equal to U2 equal to 0. So this you view as unstable locus. And you take the complement is a stable locus, and then they can actually quotient the GIT quotient by C star. Okay. So basically you cross the original state before the GIT by P1 and do a skewed or group action, and then you do a stability analysis. You get this one here. The point is that I have T equal to C star action. And what is a T? So C star, if I put this T here, T is acting on Z, W, U1, U2 is going to be equal to Z, W, T, U1. I'm just scaling a P1. Okay. So I get a W, I get a T action on this one. Actually this is the center. So here is the key point. I construct a space which has a C star action. Now what is good about this one is the next statement I'm going to write to you, is that if you look at the fixed loci of this T action, the C star action, it is exactly going to be a copy of this one, C5 cross C, and C5 cross C minus 0, C star cross, and one more thing is that this is going to be the case where you have a Z equal to W equal to 0, and U and 1. So this I call it. Okay, so you're going to review the detail later, but the point is that I want to understand how these two spaces are different. In particular, the big question is that if I have a cohomology class, say I for one differential form of this space here, and I have a two homology class on C5, Z5, and I want to understand I for one of this, okay, just minus I for two of this equal to this is the wall crossing term, right? This is a numerical wall crossing term. I want to understand how to write down what is this wall crossing term equal to what. I mean, I want to calculate this one. So the one method is just like this, is answer or approach. That's going to be equal to a class inside the master space. Equivariant. This is equivariant. Such that alpha is strictly equal to alpha 1 and alpha 2. I mean, we're not going to compare two completely independent classes on these two spaces and say what is the difference of their integration. Okay, don't mind it, this is open, okay, just sort of test the idea. So these two classes has to be connected, somehow related, so have to be universal. If it's universal, it can always be lifted to a T equivariant class over the master space. Okay. Now once you get this one here, then what you do is you integrate. Okay, so here is the check. You integrate now. If you look at this is the so the degree of this is the same, but the dimension of W is one complex dimension bigger than this, right? So we'll go to this one, coupled with C1 of the trivial vector bundle with weight 1. So I mean, this is all it's a generator inside H2 T of a point. Okay, it's unequivariant, it's a trivial line bundle, but equivariant has non-trivial action. If I do this one here, and this is like pushed to the non-equivariant cohomology, I take degree 0, because of this factor, it is always equal to 0. And because this is an equivariant class, and I apply the equivariant localization formula, and it will in C5 minus 0 cross C star, and then it will be this alpha union with C1. And this, if I put this as U, belong to H2 point. So this is just U. And if you look at the normal bundle, it will be U here, and then plus the other one. That will be alpha. This is C1. That will be minus U. The way the normal bundle actually is exactly opposite, and then plus integration from home. And this one will be the alpha 1, and this one will be the negative alpha 2, and I have 0 on the left hand side, and the difference, the wall crossing term, is calculated by looking at this. So this is the wall crossing, numerical wall crossing by master space technique. So it works for almost all simple GIT wall crossing.
Where does this W come from? Is it just by constructed by hand?
Oh, you just like
there's some intuition for why this W is.
I don't want to guess. It's kind of simple, but I learned from the work of Michael Saris. But that's so it's somehow the two GIT quotient actually turn out to be the two fixed loci of the C star action. There will be a little bit more, so now we're getting the. Okay, so now here's Hygiene. So this is the story we're going to tell next. Okay, now we want to do the Gromov-Witten invariance, right? And Witten says it's going to be a wall crossing, and Witten actually specifically says that the wall crossing will be sort of try to understand the Witten and guess. So now we will try. So what we will try a field theory. C5 pick out 0 cross C quotient by C star. Okay, so let's try a field theory varying in this. Okay, I have a simple-minded understanding of this line, or if I'm not, I should say this is, understood as the way I understand it. So what is a field theory? Field theory is going to come with, have a base. The base is allowed to vary, so it's have the nodal curve, and field theory has to have a line model. And the line bundle is associated, so this has weight 1, right? This has weight -5. So each copy of C, the number field theory means I have to associate with a section. So these are 5 same copy of C, so I have to have 5 sections. These are the section of L. And this is the same copy because C acts on the same, but this has -5 weight. So I have another section, so rule should be, priority should be E is -5 because the line bundle I think of in the ideal case, I allow to scale the line bundle. So this minus should be this one, but it turned out not. So we have to cancel with the canonical line bundle of C. Now this, the physicists, we learn from the physicists. You know, they say there is a couple with gravity, which I don't understand why, but it works. Okay, just amazing. So I just look at this. Okay, now I have this data, right? Subject. So I 5, 1, 5, 5 should be never 0. Plus stability. Stability meaning automorphism equal to 0. And then I consider a stack of this thing. What is the arrow between the object of this one? Arrow where B C goes to C is automorphism, and the line model allowed to scale, and the section will scale according to the line model. So you can construct stack, and what I want to say is that I want to say the moduli, so the moduli of stable such field. This is unquote, is defined to be, I call G. G is the genus of G, and P for D. D is the degree of L, and I put P here. Why? It's almost like stable map, but I say I put a P, I call it P field. Why am I saying this one? Because if I have 5 sections which are never 0, you see, I have a F, C goes to P4. This is just going to be C, L, 5, 1, 5, 5, right? I mean, this data give a stable map, and once we have this one here, then rule is just going to be, now the L becomes the pullback of O1, so this will be F pullback O minus 5 cancel inverse. Okay, now we want to do so we do this one, and it's a 3-manifold stack, but for G positive, this is not a proper stack, but nevertheless, it's a 3-manifold. Okay. It has a perfect obstruction theory. Why? Because it is perfect relative to a pair of curve and line model. Because once we fix the curve and line model, we're just talking about deformation of section of line model. The first order deformation is the H0, and obstruction is H1, and the base is curved, so normal high edge, so it's perfect. Okay? So we can get a perfect obstruction theory, and we can even calculate the virtual dimension. I prepared, but I'm going to skip it. It's very easy. If you go ahead and calculate the virtual dimension, you have to add the dimension of this one, and you add the H0 of this one, subtract the H1 of this, and what you get a virtual dimension G P4 dP actually equal to 0. It's a 0 virtual dimension. So now you're going to get a virtual cycle. A0 and RG P4 dP. Okay, so we get a virtual cycle. And now it's a degree 0, so I'm just going to take the degree of this cycle. Yeah, define N, G, D, put a P here, to the degree of N, G, P for D, P. And the theorem join with Chen and myself. Now, if you're a physicist, I mean, you get some number, which depend on P4, depend on genus, depend on degree, and depend on the field. The field, does it depend? it does not depend on anything else, but depend on this 5. What is the case? What's the candidate of invariance? Dimension 0 invariance that depend on genus degree P4, and there's a 5. It's the quintic Gromov-Witten invariant, or Gromov-Witten quintic, which is, and the theorem says that MGDP minus G plus D plus 1 MGD. So this is of okay, so how are you going to understand? How are we going to understand this? I mean, the way we understand this is we say this is the field theory value in X. Okay, so here that's a catch. Okay, so remark. This moduli space is not a proper moduli space. Okay, so I do get a virtual cycle sitting inside this. I do get a virtual cycle, and because this is not a proper, I'm not allowed to take degree. Okay, it doesn't make sense. Okay. However, so we have to use a different technique. We call possession localized virtual cycle, done by Kim and myself. And we actually show that this is actually a cycle. I mean, this is useless. Actually, it's a cycle inside A0 and R G Q5. Look at this. I mean, once we realize this is a cycle inside this space, it gives you every indicator it must be somehow related. And that's all. Okay, so I'm not going to talk about this, but the conception. Okay, now we're going to go ahead. So once we did this one, we sort of, okay, so there is a chance we're going to do the Witten's, the division that we're going to do a wall crossing of Gromov-Witten and the FGRW LG space. And the point is that we're going to build up on the master space here. Right? We're going to build on the master space here. So now the next thing is we're going to work out. I want to keep the master space, so I want to keep this space. That's very easy to work out next case, right? So what is the field theory? With value in C5 cross C5, C minus 0 crossing C star. I mean, that theory is supposed to be wall crossing with the mirror of that theory. And this theory, we're just going to take a C here, Riemann surface, and we have a line bundle, right? And the field lines of this one here. So this is a 1, this is minus 5. So I still have 5, 1, 5, 5. These are the same 5. And then the root here, the same exactly, except that I want the root to be never 0. Now, root is a section of one line bundle. This is a 5 section never 0, saying they have no common 0. But root never 0, this is the same as saying that root is inside this, right? So root actually gives you L5 isomorphism to omega c, right? So this is a 5-spin curve, right? This makes CL root a 5-spin. So I take fifth root of the canonical line bundle. You know, if canonical line degree is not divisible by 5, I have trouble doing this. Then I have to borrow the idea from Dan and his group. You know, we have to do a twisted curve. So I have there. I put mark points here, and then this one will be a pointed twisted curve. I started learning this when I was working on this It's quite tricky. A lot of little things you have to be really careful and still learning. So this is the orbifold curve, and orbifold happens around the marking or the nodes. And these are, this is locally free orbifold sheaf, locally free sheaf, and the section, and this one. And once we do this one here, then we come up with the modularized space we call M bar. So let me put G gamma. Okay, so that's 1/5 5P. Okay, so this is the modularized space. Let me just explain. So sigma here, if I have a L marking, so gamma equal to gamma 1, gamma L is a monodromic of L along sigma. Okay, so there are L of them, and so this is the marking. This is 1/5, and 5P meaning that I have 5 fields. Okay, usually, when you do the spin curve, you just take this out. But here, we're doing the fields. If you without field, this is a smooth step. So the virtual cycle, what do we mean by virtual cycle? It's just a cycle. But once you get a field here, then it becomes virtual cycle, even though you have section have a abstraction space. Okay, so you do this one here, and the upshot. Let me erase this. I just want to keep this one here. The upshot is that the virtual cycle G gamma is 5P. I have to do the localized, the cosecant localized virtual cycle. This is called the LG3 FGRW, or we call FG series of C5 quotient by C5 of this. So one of the FGRW series probably is associated with this particular case. Okay, so I have reconstructed Gromov-Witten invariants, and this. The point is that I've been working on the virtual modular space. The modular space, the Gromov-Witten of quintic is, I say, it's a highly nonlinear series, right? Because we're really looking at the space of map goes to quintic, which is quintic, right? It's not a linear space. However, the series we construct here, we only look at the modular space of, these are purely sections of line model. It's like map goes to projection space. I'm just talking about sections. And this is also talking about going to sections. And the quintic is hiding inside of the obstruction series, but it's not touching the modular space right away. And these two modular space, these two series, the Gromov-Witten and the FGRW-FG, is only by making the non-degeneracy condition somewhere different, right? So two different GIT. One is I'm making the rule section nowhere vanishing, the other one I make the 5 section up. So this becomes that goes to P5, and this becomes spin. Okay. So now I wanted to say that Gromov-Witten of Q5 and FJRW of C5 will cross. Okay, so the way to do it, we're just going to work under the master space. So the master space, I just erase the master space. So the master space is going to be, remember, it is going to be have a C5 cross C. Then I add 2 more copy. I have to subtract all of these things.
It's in the middle.
It's in the middle.
It's still in the middle? Oh, it's still in the middle, yes, yes. Okay, so, good. So now you can construct the field series yourself, right? Oh yeah, so it's Z1, Z5, W, U1, U2, and this two has a C star action, and this two coming from the same C star action but with different weights. So any particular C star action has to associate a line model. So I have to have two line models associated. So what is the field theory? So I have a C, now I have to put a marking. Okay? So I'm going to have a symmetristic curve. So I'm going to have two line models. And then this is the same line model, so I'm going to have phi 1, phi 5, and the rule. It's just like this. And the non-vanishing condition, you just interpret the non-vanishing condition like what I did here. And then you add two more sections, I put U1, U2. So phi rule as before. And but on U1, I want it to be global section of L tensor N, right? And the weight C also acting on this, right? So there's an L inside this. And then the U2 is H0 of N. And plus the constraint. So I'm not going to write it, just like you can interpret that. And once I get this one here, I can write down the, so there's a genus, I can write down the moduli space of stable fields like this. It comes with genus G, which is the genus of a curve, and there's a marking along the monogamy along the marking. So I put the S D gamma here, and then I have D, which is going to be degree L tensor with N. There are 2 degrees of line models. There are two degrees I have to keep track of. So this one here. And I can construct this one. This is a Riemann manifold, finite type, locally finite type, not finite type. If you do relative obstruction theory relative to this data, we're only talking about sections. So it's a perfect obstruction theory. So I get a perfect obstruction theory. So I'm going to get a virtual cycle, but this one is non-compact, not proper. So I have to use the cosection to get a cycle. G, gamma, D, virtual, local, inside, A star, T. Okay, I'm going to talk about D bar. And what is the T star action? I imagine that I have an extra T star action here, right? So T is going to be T, phi, rule, U2 equal to, everything the same, I just scale the U1. Back to T star. So this is something inside this, this is so the upshot is that I get this one here. So what I'm going to do with it, just like what I did in this case. Right? What I did in this case, I take some cycle class, and then I multiply, I just erase it. I lift this class to a covariant class to W, and then I multiply this class by the trivial class, the trivial class, and then I integrate it, and then do a localization formula. Okay. So now, let me just say, in case gamma equal to 0, in case I look at the modulus where I don't specify marking, okay, there's no marking, then I get this one, the virtual dimension, WG, empty marking, and then D0, D, actually D infinite, equal to D0 plus D infinite plus 1 minus G. Okay, so this, you see, it's not necessarily positive, but often it is positive. So in case when star is positive, so what I'm going to do, I'm going to do a class, U is the generator again of H2 equivariant of point. I do a star here. Okay, let me put the delta here. So with delta positive, I can delta here, I can do a virtual cycle, G empty set, G, and I took it at 0, to 0, I'm going to get 0. So I get a lot of identity, okay? Because if G positive, only for few, so the meaning for D is going to be D0, D infinite, equal to D0 or 0 D. So almost all of the D I get positive, only for very few number in the very beginning. So I get 0, and then 0 is what? I have to apply virtual localization theorem.
Why do you have the equation that this is equal to 0? Where does it come from?
Oh, this one. This is the C1 of the trivial line.
Why is it 0? The question was why is it 0?
Because it's a trivial line. When you reach to the non-covariant theory, you get a 0 factor. No, U is not true. U has is the trivial line model with weight 1 is an invariant theory. It's a generator of yes, this that's probably a better explanation, but that's the way because if this is positive dimensional cycle, I can cut with the co-cycle to bring to dimension 0 invariant class, and then I can take it push to the non-covariant theory. You always get 0. Okay, so this is the 0, and this is exactly the 0 in the ordinary wall crossing case. In an ordinary case, you have a cycle where you lift the master space, it is always 1 degree lower than the dimension master space, so you can always add C1 of trivial line. So this is the one here, and then you use the virtual localization formula. How much time do I have? 10 minutes, good. I speak it quite a few whole session. I want to let you have a feeling what we are getting, right? So this is going to be, okay, I can just write it down here. It's very easy to write it down, but to decode the information takes a long time. But nevertheless, let me say gamma, normal bundle, W gamma, W virtual, W gamma, maybe put local. So these are the pixels of this. So now, let me just elements in W gamma. So it's like, when we say we can do localization to understand the modular to Gromov weighting invariant of stable map to P4. We do the localization, then we have to understand what are the T covariant map. Okay, these are high genus curve, always go to vertex point, and then they connect by these covariant lines. What about in this case? Okay. So there's okay, so let me put this example. Okay, so I have C, L, mu1, mu2. Now if mu1 is identically equal to 0, what do I get? Right? So, I mean, you probably remember phi and mu1 never 0. I mean, that's this stability, I mean, the GIT requirement, which actually means that C phi is actually mapped to P4. If I impose this, I get this is never 0, but also I get mu1, mu2 never 0, right? So u1, so u2, so u2 equal to 1, so n equal to O. And that's the trivial line model. And then there's okay. And because this T covariant, well, this is because the action is acting on V1. But if V1 is identical to 0, I mean, this is equivariant, so phi is rooted arbitrary. But that's exactly the FGRW imbalance. You see, if we do master theory, if we analyze the fixed loci, we should be able to get the theory of the fixed loci itself. And this fixed loci is associated to the FJ, and so that's the energy theory of FJ. And if I do example 2, mu 2 equal to 0, oh no, this is not F, this is a global filter. I have a map, and the field is arbitrary. And if I do mu 2 equal to 0, I will have mu 2 is associated to rho, mu 2 is never 0. So basically rho is equal to 1. That's the spin case. Okay, that's the spin case. And then mu 1 is equal to 1, and this is going to be LG. Okay, so the example. Elements in this is T quadrilateral elements. And then there's another case is that mu1, mu2 are non-zero. Okay, I assume that the base is irreducible. Okay. Base irreducible, C irreducible. But I am scaling the V1, U1. Right? If I scale the U1, I still get invariant. Then I should be able to cancel the scaling by scaling the line model. Right? I mean, if I allow to cancel the scaling by scaling the line model, then the section, other section of that line model has to be vanished. Right? I mean, the other section has to be invariant of this section. So this has to imply phi equal to rho equal to 0. So what are these modular space? These are just going to be M bar G, G different G. I mean, I don't have any other fields. But these are not never, beyond 0, invariant imply mu1 equal mu2 equal 1. So these are just the ordinary. So what I want to say is that there will be some numerical numbers coming out of this modular space, but these are the ordinary Hodge integral modular. So these can be calculated. So we already see FDRW, we already see global Witten, and we also see the Hodge integral. And now let me use this one. So the last picture, and you need to see that so you get interested. So what in general I see, C is going to be some curve, maybe not just draw. There's many irreducible components. So what I want to draw is that there will be maybe some component here, and maybe some component here, and maybe some component here. Okay, so the point is that mu2 restrict to this one here are identical to 0, and mu1 restrict to here are identical to 0, restrict to here, mu1, mu2 restrict to this component are identical to 1, and these are C1. And usually this has there's a marking here, and there's an orbital denominator here. So what I want to just verbally say that this you can organize the fixed loci by a decorated graph of this kind of geometry. And this class, you calculate this class, will be the product of the, so this will be this will contribute an FGRW. So you take the curve curve out, and you have to insert back the marking points. So you're going to get FGLW of this particular genus with the prescribed monogamy. So FGLW here and FGLW here. So this is our FGLW invariance. And you have this will be Hodge integral. And you take this P1 out, you get marking, but this is a Hodge. And then you take out this one, this will be Gromov-Witten of Q5. And this is, you allow point to be very here, this is a final zone. So eventually this one will be the product of this one multiplied by this one multiplied by this one. Okay, and each of this will be a product involving Gromov-Witten, FGLW, and Hodge. And this term can be calculated by knowing the order, degree. These are P1, so these are calculated. So you get a sum, you get a polynomial among the Gromov-Witten invariance and the FGLW invariance, and you get 0. And you get 0 as long as you get this plus this is positive. The choice which we can try is try this and this. So let me, I've just have half a minute, so let me just state the first thing you can get out of this one is 0. With delta positive, it is delta, and d bar equal to d0. This implies that we can recursively evaluate based on your genus degree and the FGLW invariance involved. And the second theorem is delta positive. And if I choose d bar equal to 0, imply I'm hiding quite a few sort of detail here, and also that's quite vanishing. The FGLW invariance in the end only involve where for the expert. This monogamy here is given by -2/5. 5 is quintic, so basically it's only zeta squared. -1 can be reduced, but other things by dimension reason we can vanish. So it is also what Witten actually conjectured. He says that the Gromov-Witten invariant of quintic should be equivalent with whatever goes to the FGLW, his class, Witten top trig class of the insertion -2/5. He specifically said that. And after more than 10 years, after proving the vanishing theory, this is also true. And also, this is also very happy surprise because if these relations are complete, then we can actually solve we can calculate FGLW with insertion -2/5, recursive everything. But there's a little thing involved. Right? There's always missing a little bit of the initial conditions. That has to be. So there are other ways. This is only a very beginning, and the things are very complicated, not surprising. So I really hope that more people will get involved with this, and eventually we can see more clearly what the height in this Gromov-Witten invariant of quintic will be. And there's so much I had to do combinatorically, how to organize this data and how to to calculate these things and to prove the formulas. And this is only the very. Thank you very much.
Questions for June?
Presumably, this is not just a quintic, right?
Someone asked me these questions, and I say yes, this can be done for other complete intersection, And then Chiodo, Alexander Chiodo, he objected. He said, for others, there might be some issue. And so I don't want to, okay, this is my answer. I believe yes, and some experts say there's some issue, and the issue coming from some vanishing zero. So yeah, that's.
So I was wondering if the equality of in your theorem was comparing two different degrees. If there is any other instance in which you can have a similar theorem, similar word crossing type theorem for higher dimensional.
Anytime you have a modulus space which has DIT quotient, you like modulus shift resistance is done before, but I guess with sort of variance field that's for the first time. But what I want to say is that the whole idea of this mask space, which is actually very effective in many of the more causal study, can be adopted to get some relations, which I don't know if that answers your question.
So I think so, is there an old case in which the equal dimension is not zero?
Which
That you were comparing two numbers, basically.
yeah.
And is it known? Is there like a
So we are not getting number only, right? I mean, as long as delta positive, if I put a U1 here, I get a zero I get a vanishing among certain classes. Yes. Actually, I mean, this actually get much more, and I can vary a lot, but I mean, I want to say that it get more than to complete, but we haven't proved it. For instance, this polynomial relation, the coefficients coming from Grothendieck and Riemann-Roch. So if we can show that the leading coefficient is non-zero, then we can say it recursively evaluate. But we hope that is true. So we want to say they are independent, but maybe for some reason they are, we don't know. But this will be clear in the